the previous video on the series of electricity and magnetism, I had ended the video with a question where I had just uh, given you a charge distribution, a linear one, and the question was to obtain the electric field intensity, the net field intensity due to this distribution, the length being here equal to L, and we were to determine the electric field intensity at the point P, which is lying at a distance, say Z, from one of the ends of that linear charge distribution. Now, we had done the other way, the other one for it, where the point P was lying along the perpendicular bisector of the length L, or 2L suppose, uh, and so that was obtained. But well, I probably had no takers for this kind of a question, so I take it on myself to solve this one, and we proceed as follows. Now let us assume that we have a small segment of it, that is let us say dx, and that lying at a distance x from this end, from where we are considering the z coordinate. So this small segment that I've considered is dx, and so this length right now, let us take it as r, where the square of r, where r square is obviously equal to z square plus x squared. That's Pythagorean concept or equation. Let this angle be theta, and so from that what we get is that we'll be having an electric field, but the electric field intensity will be obviously acting along this line. Considering the positive charge distribution, the electric field will be along this line, that is along the line uh, of that element. Now that small element will have dE as its electric field intensity acting along that direction. However, we can just take the components of it along the Z and the X directions. This is now this will obviously make an angle theta over here, and so this is simply dE cos theta, and that is acting along the Z direction, and we have dE sin theta that will be acting along the X direction. Actually, if we are taking the X as positive along the right hand side, so dE sin theta acting towards the left is actually in the negative direction, negative X direction. So this dE vector that we have over here, that will be equal to minus dE sin theta I capped, because I cap being the unit vector along the x direction, and the negative sign suggesting that it is acting exactly in the opposite sense, plus the vector dE cos theta k cap. So this is k cap being the unit vector along the z direction. And now, in order to have all of that, what we have is the value of dE. Now dE is for that small element. Let us just give you the value of the magnitude, so as to say it is k, that is the constant 1 by 4 pi epsilon naught, the electrostatic force constant k, and dq, that is the charge carried by the small element dx, as we had done previously. The charge distribution here is lambda, linear charge distribution, so lambda times of dx gives me the dq amount of charge that is contained in it, and that divided by k, q divided by the square of the distance, that is r squared. Now r squared is obviously, as you know, is a z square plus x square. I'm writing it directly without any hesitation, as we have done this previously. Now this is dE. However, for the values of sine theta and cos theta, we will be considering that triangle that we see over there, that right angle triangle. This is that right angle triangle. We let us just name this triangle here. We name the point O. This is already the point P, and let this be Q. Q, you may confuse it with the charge, so I would probably give it a point M, suppose, right? So OPM is that, sounds a bit odd, OPM is the right angle triangle, and from that we have the value of sine theta. The value of sine theta is simply equal to the perpendicular divided by the hypotenuse, that is x divided by r. Remember, r is simply z square plus x square under root, so z square plus x square under root is z square plus x square to the power half, and that when multiplied with okay, we'll be dealing with it later. Then we have cos theta. We have the value of cos theta to be equal to simply z divided by r, the value being z divided by z square plus x square to the power half. Now if we use these values in that above equation that is right here, what we get is dE simply is equal to minus, instead of dE we have k lambda. We can save the dx for later, because we have that x to be put for sine theta. We have z square plus x square. That was there, but again with this sine theta being multiplied, you have a x in the numerator, and z square plus x square to the power half, when multiplied with this simply goes to 3 by 2. In case you're having any problem with this, you can just multiply that and see for yourself that you will end up with this, but shouldn't be a problem though. So this is dx then, and we also have the I cap. This is negative direction, the minus sign has been put over there, and then we have k lambda. The dx can be taken later. We put the value of z for that cos theta over from this, and in the denominator we have the same result, that is z square plus x square whole to the power 3 by 2, and this is simply k cap. Now the net field intensity obviously can be integrated over. Now this bit that we see over here, this was done in the previous video. You will have to look for it. It is in this playlist, of course, so I'm not wasting any time further in doing that again and again. And how do we integrate this? Well, this is being well, we have the dx over here. Now the dx is being integrated from this end, that is from the point O to the extreme end. Let me name it as n, from the point O to the point n, and as it moves, the value of x changes from 0 over here to L over to this point. So it varies from 0 to L. Now E is simply the integration of dE, which in turn is the integration of these two terms that we have over here, over the x direction and the z direction. Well, because both of them are integrated over x, the second term over here, what it results in is that it results in a value like L divided by z root over of z square plus L square. You can check this for yourself, as this was in the previous video. So I'm not really wasting any time on that, but I'll definitely deal with the first one, which was the thing that we need to look into. The k and the lambda, being common in both the cases, have been taken outside, and what we are left with in the first case, this entire thing is in brackets, square brackets. The first term over here, what we get is I cap stays as it is, and we integrate this term from minus x dx divided by z square plus x square whole to the power 3 by 2. Now Well, if you look at this thing, that is r square is equal to z square x squared, and if we just differentiate it, what we get is 2r, because r square is 2r, dr will be equal to, now the z factor that is there, that is constant because the value of z does not change as x varies. Does it? Well, it does not, because here only r is dependent on the value of x, and the x is the value that is changing. Z is not changing over here. So obviously any derivative of any constant term is 0, so that of z square is 0. But what about x square? Well, that is 2x times of dx. We can get rid of the 2's because this thing is not there, right there, not right there. So so the 2's can directly get cancelled out. What we have is x dx to be equal to r dr. Now we get to a value over here which tells us that we keep the negative and the integration. Now as x is 0, for x being equal to 0, we set the limits now, because we are taking the value of x from 0 to L, right? And in that case the value of r, because now we'll be putting the value, instead of x dx we are putting r dr, because that is what we have obtained over here. So r dr, and the denominator, as you know, z square plus x square was equal to r squared. This becomes r cube, and the limits change. Well, when x is equal to 0, what is the value of r? We take this case into account, that is, I rewrite it over here, that is r square is equal to z square plus x squared. So when x is equal to 0, r square is simply equal to z square. So, or we have r to be equal to z, right? So the lower limit, as x goes to 0, we have r to be going to z. And then for x being equal to L, we have z square plus L square to be the value of r square, or simply r is equal to root over of z square plus L square. And we take it like that as it is, without any hesitation. So L square plus z square under root, and the I cap stays as it is, plus the curly bracketed term in k cap. I'm not repeating it. So k lambda is as it is, and this minus term stays over there. Now r, one of the r can get cancelled, and we are left with r square. Now the integration of r square is simply r to the power minus 2. That is, the integration of r to the power minus 2 dr will be giving me r to the power minus 2 plus 1 divided by minus 2 plus 1. And this minus sign gets cancelled. If you are good at integration, you will just find that this just ends up with 1 by r. Again, uh, you have to be a bit vigilant about what has happened, because the integrations are mathematical things, and I'm doing them directly because I expect you at this level to be thorough with the integration part. In case you are not, you may consider the kinematics integration formula that I have discussed in the kinematics part quite early in my video making. So now with the limits done and dusted, you just put them right there as they should be, and this is equal to 1 by L square plus Z square under root. They are the upper limit, and this is 1 by Z, that is the lower limit, put in place of R. Well, this was in curly braces, and we have an I cap over there, and again a set of curly braces where we have L divided by Z, and Z square plus L square under root in the denominator multiplied with Z, K cap. So this is the form. K lambda is common for both of them. This is the form of the answer that we will be getting in this case? Well, you can, however, see that I cap and k cap, because they're perpendicular to one another, you can just take the square of all those terms and then get along with that once again and find a proper answer for your result. But that, well, this form seems tidy enough, so we are restricting ourselves to this form. So that is what the answer looks like for the question that I had given you. uh, as I said, I didn't have any takers for it. Probably I didn't receive any answers, so I take it on myself to do it as I had promised. And then we move over to the next part, which is the electrostatic part, that deals with Gauss law, as well as the electrostatic potential, electric flux to begin with, before the Gauss law. Let's begin with that. Well, at a very basic level, you might have come across the term flux, and so as to say the electric flux. But before that, we must discuss a bit about the electric field lines. Now, the electric field lines are the lines along which the electric field or the electric forces act or tend to act, and that is why they are popularly known as the electric lines of force. They are just simply imaginary lines. Now, if I have a charged particle over here and I leave it in isolation, then I sprinkle or I drop a test charge, suspend a test charge over here, just to see or observe the force that it is acted upon by this charge that was present initially. What I'll find is that this force will tend to push it along a line, along a certain line, and same goes with this place as well. I place it over here, and this tends to push it along that line. So definitely nowhere in between, though. If in case I tend to place it somewhere in between, then that will obviously be along a certain line as well, but it won't be you know pushed sideways from its along that line, not here, not along this, but completely along the radial path, so as to consider that this charge is at the center of some spherical distribution or spherical uh, sphere of influence. Now, from that being the center of that sphere, and that sphere is its own sphere, it is its own influential area, which is of course what we learn as the electric field. And that field extends with greater distances, but obviously it gets weaker, as we have studied that electric field is inverse of the square of the distance. So that field intensity tends to get weaker, but nevertheless that acts along these lines which are acting radially outward. It will be just the other way around if I consider a negative isolated charge, where if I put a test charge. Now remember, usually the test charge that we consider, they are always, most of the cases, they are considered positive. So positive test charges that are considered, it will be attracted towards this charge along the radial path. So what we can make out from this is that the lines of force in case of a negative charge are directed radially inward towards the charge, while that for a positive charge are directed radially outward. And there are various properties, of course, related to the electric lines of force. They never intersect each other. They are continuous straight lines. They do not form any kind of loops, and so on. The concentration of these lines obviously gives us the intensity. The greater the concentration over a given area, the greater is the intensity of the electric field. So this electric field intensity that we usually represent with the letter C, that we have been studying of late, that electric field intensity is simply due to the greater that intensity is greater in case the field lines concentration is greater over a given area, which is quite obvious if you observe this this isolated charge, or even this negative charge. The concentration was greater over the area closer to the charge, and as I take the areas away from the charge, the concentration goes on decreasing because the lines tend to diverge. So as a result of that, what we find is that the electric field intensity goes on decreasing, the concentration uh, goes on decreasing, and so does the electric field intensity. Now, the number of lines of force that can be incident over a given area. Now, suppose we have the electric lines. These are the electric lines, and imaginary, of course. They give you the concentration of the field. Now they are incident over a given area, so as to say this, let this be the area, and the number of lines of force that are associated, number of lines of force, instead of associated we use the word linking with that surface, number of lines of force linking with the area, that gives us the amount of flux associated, which is popularly or usually denoted by phi subscripted with E. This is the electric flux, which gives us the number of lines of force associated with that given area. Now, just prior to this, what I had mentioned is that the number of lines of force, or the concentration, I had used the term concentration over a given area means the number of lines of force, and the concentration of it is obviously over a given area. So the number of lines of force over a given area, they tell us about the intensity of the field. Now so the number of lines of force that are associated with that area can thus be obtained by just cross multiplying this, that is electric field multiplied with that area, is somewhat giving me an information about the number of lines of force. And that is how we define the electric flux, isn't it? The number of lines of force associated with that area is what we are talking about. So the electric flux is equal to the, now this linkage that we have over here, that is the lines of force linking with that area, that linkage has to be proper. And in terms of proper, what I mean is that they have to be spread, or they have to be linked with the maximum possible area, and for that to happen the surface must be perpendicular to the given lines of force. What it means is that if I have, let us say, the shape of an ice cream cone, and in this cone I have the flap, the lid of that cone, usually thin paper that is put over that ice cream cone to protect it before use. Then I have a solid angle associated with it. This is the solid angle, and the solid angle usually denoted by omega. And here I have the charge. Now the charge has an electric field exactly radially outwards, pointing exactly radially outwards. And this electric field pointing radially outward is not exactly uh, or wholly linked with that flap cover. And so this cover it is somewhat the area vector of that cover, let it be ds, that area vector is pointing along that direction. So there's an angle associated over there. Let that be equal to theta. So in order that this flux linkage is wholesome, this area vector has to be in line with that electric field. That means it has to be along this line, or conversely, the electric field has to be along that area vector. So that means that when we have such a condition that one of the vectors, we have two vectors and one of the vectors must be in line with the other, which is the case of the work done by a force in terms of the displacement available. So in that case, what we find is that we lose the direction completely, because the direction is not definite in that case. And so from two vectors, what we obtain devoid of that direction is the scalar product, that is the electric field dotted or dot product with the area vector ds. And that obviously, because being a small area, surface area, gives me a small electric flux d phi e. And in case you want to, or you wish to obtain it in terms of the angle, the solid angle that is present over here, let me give you an idea of the solid angle. Well, in case of this circle two-dimensional case, what we find is that we have an arc instead of a surface area. For a circle, we have an arc, and that arc length is simply this AB, supposedly an arc length subtended by an angle theta and of radius r. So r multiplied with theta is equal to the AB arc. This entire thing has been discussed in the electrostatic portion that I have uploaded in my video segment. I'm just discussing it in a quicker way for you to get the essence of it. And then for in case this is a sphere, instead of that arc length, you will have a surface area. Instead of arc, you will have a surface area just like this one, and that will subtend what we call as a solid angle, just like over here. And the surface area is associated with the solid angle. The total area is 4 pi. If this is the radius r, then the total area is 4 pi r square, just like the total circumference in this case would have been 2 pi r. Why? Because 2 pi is the total angle in this case. So the angle multiplied with the radius is giving me the total circumference. Similarly, the total angle in case of a solid sphere, three-dimensional case, that is this angle 2 pi and the other angle 2 pi, which is taken in the other plane. This is one angle. If I am to draw it clearly, this is one plane, that is the supposedly the xy or xz plane. Then you have the yz plane to be like this. So this is 2 pi and this is 2 pi. So 2 pi and 2 pi add up to 4 pi. So the total solid angle is 4 pi. That multiplied with the square of the radius gives me the total surface area. Similarly, for this small angle d omega, subtending solid angle, of course, subtending a certain area ds, we have d omega times of r square is ds. But this ds, as you know, was offbeat. It was at an angle theta. It was not setting on that surface. So in order to set on that surface, it has to be taken the cosine of it. So that means ds cos theta in general is equal to d omega r squared, or the r squared can go down. So you have ds cos theta divided by r square is equal to the solid angle. This is a very important relation. In case you didn't understand this, you can just go through what I have explained just now once again, you'll know what I'm talking about. Or in case you want a detailed information about it, you can go to the electrostatic segment of my video list, and you can learn this from there as well. Now E dot ds, now let's just get back to the topic. So this is the amount of flux that is associated with the segment or the section ds, which is acted upon by an electric field, let it be at any angle whatsoever, that is dealt with by this dot product of electric field with that surface area. And therefore all you have left is the magnitude, which is the number of lines. You are just left with numbers and nothing else. Now with the concept of flux done and dusted, we can just move over to the theorem which allows us to obtain the flux that is linked with a closed surface enclosing a certain amount of charge, and that is the Gauss theorem. But what we will be dealing at this level is the Gauss theorem, is the differential form of the Gauss law. What the Gauss law tells us is that the flux, the amount of flux that is associated with an enclosed surface, let it be of any shape, not necessarily spherical. We have the spherical symmetry about the charge, around the charge. So as we obtain the value or the integration, it will be obviously throughout that entire spherical region about the charge. So it is not really concerning if this shape is a sphere or any potato shape, doesn't really matter. So what the electric flux tells us is that, or what the Gauss law tells us about the electric flux, is that the electric flux is equal to the amount of charge that is contained within that given surface divided by epsilon naught. Now there's one more thing that I would like to suggest. In many of the books, what you may come across is that this derivation, I have done this derivation exactly how it is in the electrostatic part. Once again, I would refer you to go through that in case you do not get this. And this is obviously the total charge enclosed within that volume. If Q is the amount of charge, then Q is what we get over here, but in general this is the total amount of charge that is enclosed by that enclosing surface. If that charge stays outside, what it does is that the lines of force that are emanated from it, that they can go in, but gradually they will be going out as well. So when you are doing the dot product at this end and this end, the net flux is vanishing for that given electric field, because in one case the electric field will be directed along the area vector, in the other case the area vector will be the other way round, and so they will be cancelling out each other when we add these two terms up. So that's the Gauss law. What I was telling is that if you look at the derivation that I have done for this in the electrostatic video, I do not remember the serial number of that video, so spare me for that. What we can also consider is that in the CGS form, the value of the electrostatic force constant, that is K, which is 1 by 4 pi epsilon naught, in CGS system, this value goes to 1, simply 1 in CGS units. And what that does is that this thing that we have over here, phi E, simply then becomes equal to, because this has been taken as 1, so instead of that epsilon naught down below, you end up with something like this, which is the case in this is for enclosed, the sum of the charges enclosed. It can be capital Q, small q, doesn't really matter. These are just denotations, but this 4 pi crops up because this is considered in the CGS system to be equal to 1, that is the value of K. that is the force constant, that is the electrostatic force constant. So you need not be confused. This and this result are exactly the same, but they are just taken in two different systems of units. I hope that will be all for this video. In the next video of this series, we'll be dealing with the divergence and the curl of the electric field, as well as the electric potential associated, which is the scalar quantity that is associated with this with the electrostatic part, or the electric charge in the static form. But till then, thank you for watching. Have a nice time.